Welcome back everybody to Section 3. Here we're going to talk about Earth's place in the solar system. Cool stuff, you know. So first, we have to talk about the solar system itself and how it formed. So going way back, before there was a solar system or anything, there were these clouds of dispersed gas and dust, really peaceful things, not hurting anybody, not near a star. But over time, due to gravity, the gas and dust starts to coalesce, starts to come in on itself, come together, but it doesn't form like a ball. Instead, what it forms is this sort of disk shape, this spinning disk that we can see in the middle slide here. This is about 4.56 billion years ago, about the same age as Earth. Earth and the solar system are at the same age, please remember this. And this continued, coalescing, coming together, flattening into this disk and swirling around faster and faster and faster until sun is born. That's what it sounded like, by the way. It's like, well, no, there's no sound in space. It's kind of a pop, though. You imagine it. Sun is born from a nuclear reaction called fusion. Hydrogen comes together to form helium. It starts a chain reaction with all the gas and dust there, and it forms the sun. Part of the reason why nebular theory is very, very useful is because it serves as a framework to explain certain things about the solar system. For example, it helps to explain why the inner planets are rocky, while the outer planets are made of this lighter stuff, this less dense stuff, ice and gas. If you're reviewing and you want more detail, this slide has a lot of detail on what this process entails for nebular theory. Moving ahead, we have this question again: what does the present have to do with the past in the solar system? So part of how this nebular theory idea came together to begin with is using very, very powerful telescopes. Scientists are able to observe faraway nebulas that are forming right now. Well, not right now, but we don't have to worry about all that. They're basically forming right now, and we can take a look at the different stages that these nebulas go through. Using the present, using what we observe here, we can work backwards and say that, well, our solar system probably formed in the same way. So moving forward, you have this question of where does the Earth come into play? What do the planets have to do with it? So some of the outer portion of the nebula, not the stuff that's in the middle that gets sucked in to become the sun, cools into these sort of swirling disks of debris that are orbiting whatever the early sun was. And there are these random collisions involved until some of the clumps get smashed into so many times that they start to grow bigger and bigger and bigger, and they get big enough to where they can pull things around them just through their gravity and sort of suck in all the remaining debris. And the result is you have these planets, these big rock chunks or gas and ice chunks, which are round due to how much gravity they have, which is a lot, and isolated because they are able to pick up everything that is around them. And it's important to note, there are actually a couple places in the solar system, we'll talk about, where there was not a planet formed. There were just these stray rocks that never ended up getting drawn in by a planet, but more on that in a bit. So, moving again back to Earth's place in the solar system, Earth is one of the planets, one of exactly eight planets in orbit around the sun. I will not fight the Pluto people, alright, I spent too much time doing this. There's also these other satellites, orbiters, moons, things like asteroids, comets, meteoroids, dwarf planets, that are in orbit out there, but don't quite qualify as a planet. You heard me. As an exercise here, you should go ahead and name the planets in order before we move on. Pause the video, do it while you're by yourself, maybe. What I'm sure you all said was Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and not Pluto. Back to this question though, why are the inner planets rocky? Well, one idea on this, and there are several, is the temperature. So there would have been such a high temperature in the inner early solar system, 3,000 plus degrees Fahrenheit, that some of the lightweight elements, stuff like hydrogen and helium, would have been mobilized, it would have been free to escape, whereas only the more dense, heavy stuff would have remained, wouldn't have been able to escape in that kind of a heat. Now, the high temperatures might have been a factor, but there's also this idea of the proto-sun igniting, alright, the big pop. It might have been so powerful, maybe, that it blew away the atmospheres of all of the inner planets and knocked that material back into the outer solar system. So for a final factor, we have gravity. And this one is sort of related to what we touched on before with the temperature. The idea is that the really dense, heavy materials would have been left behind in the center, unable to escape. There would have been all this gravity that brought it in, and the heavy materials wouldn't have been able to escape the way that the light stuff might have been. And as a result, you have this heavier stuff, the rocky materials that make up the inner planets, staying close to the center of the solar system, and the lighter stuff which gets pushed further away. I have included some links here, a PBS article about how the inner solar system formed in case you want a little bit more detailed, different explanation. I have the solar system song for anybody who needs it, and we also have a video here explaining a little bit about why the inner planets are rocky and the outer planets are gaseous with a little bit more detail than I've given you here. Okay. Don't leave. Next session we're talking about the interior of the Earth. Looks like that.